Okay, so I suppose I'll get started. Uh, Good evening. I welcome the viewers to this problem solving and live interaction session for the subject Strength of Materials offered by Professor K. Ramesh on the SWAYAM portal. So, the idea behind this session is to have a comprehensive recap of all the contents that have been discussed throughout the duration of this course. So, there will be problems that I will be solving starting from week 1 to week 12, ranging through various topics across the course, which is to serve as a recap for the students taking the exam. So, for those who are watching this for the first time, let me briefly introduce myself. My name is Ganesh Ramaswamy. I'm a doctoral scholar in the Department of Applied Mechanics and Biomedical Engineering at IIT Madras, and I'm working under the guidance of Professor K. Ramesh and Professor U. Saravanan from the Civil Engineering Department. So, for the videos that were previously recorded for the other sessions, that is session 1 to session 12, uh, one could navigate through the SWAYAM portal page, or it is also one can also scan the QR code on the bottom left of the screen, which will take you to a channel where those videos are uploaded, where viewers can watch it at their convenience. All right, so with that, let us look at this first question of the day. So the idea is not to solve everything threadbare today, because the problems will be ranging from week 1 to week 12. Naturally, it might not be possible to accommodate everything to the end of the solution in a 2 hour session. Nonetheless, I'll try my best to do that. So the idea would be more on the discussion of the concepts that were involved in solving the question and the nuances if there are any. All right, so we have been given a setup such as this, where we have a block of mass m. Actually, it is already given that it is weighing a rigid block, rigid being the key word, meaning this block does not deform. So that is to be noted. Weighing W kilonewton is supported by three symmetrical rods, supported symmetrically by the rods. So we have one rod that is made of steel of length so and so, area and Young's modulus is given. And then we have shorter copper rods on either side, which are symmetrically placed. The allowable stress of copper and steel are 70 MPa and 140 MPa respectively. It is given. So the allowable stress, that is, if it were to go beyond this stress, we would consider that the constraint has failed, and so has the setup, the arrangement. So our idea is to design safe structures which are well within the allowable stresses. So it is desired to make this assembly carry the maximum weight W. So for anything, there is an investment involved. So naturally, our aim will be not to compromise on the safety, as well as maximize the exploitation of the material, so that we can build structures economically. So there are two aspects to design. There is one is safety, which is not negotiable at any cost. And then there is the economics. So there must not be too much redundancy that it goes beyond budget. All right, so answer the following questions for such a condition. So the condition being that we want to maximize the weight of this rigid block, W. So the magnitude of stress developed in the copper rod, magnitude of stress developed in the steel rod, and the weight of the block, of course. The maximum weight, what it can sustain is what is asked. So let me just take a copy of this. So let us see how to go about solving this question. All right. From here, from the question, it is known that this block is rigid and symmetrically supported. So let me draw this block once. All right, so I have the block like that. And then of course, I have the three. Let me put it in some other color, maybe. Oh, let this be red. For the supports, I'm using a red color. All right, so far so good. So let me take this out. if I were to take this block out, oh, it is coming as one, just a moment. And let us say it is supported like that. It is supported symmetrically like that. So our initial procedure is to take the setup and dismantle it into its components. So this is anyway supported firmly on the base, on the firm base. So what I'll do, let me take this block, separate it out. So let it be like that, and let this be like this. So we have separated it out. So naturally there will be a force interaction. So let us say that this is copper and this is steel. So we will refer to it with those subscripts. All right. So this offers a force, a reaction force on the block, by virtue of which it is supported, it is in equilibrium. So this, let it be R. Let this be RC. Now, by virtue of that being symmetrical, we know that the opposite, this thing will also be RC on the other end because it is symmetrically supported. Let us say if it was lopsided, if this block was extending like that, then naturally these two reactions will not be the same. But we have the recipe to find it out by our engineering mechanics. It is basic equilibrium of rigid bodies. So I'm exploiting the fact that RC is the copper rods are symmetrically supported, symmetrically placed, by virtue of which these two are equal. And now let us say we have this as the reaction from steel, like that. Now one common mistake that might arise in students is they might think since it is symmetrically placed, all the forces will be equal. So that may not be the case. That will depend on its stiffness. All right. Have I missed anything in the free body diagram? I obviously have to account for the weight. So this is downward W. All right. So this much we know. And we know that this entire block is actually in equilibrium. So I have accounted for all the forces now. So let me do sigma Fy equal to 0. So what does this gives me? What does this give me? This gives me a condition 2Rc plus Rs is actually equal to W. So I have got one condition like this. One condition like that. Now let us draw the free body diagram of the other pieces. Now we know once I have put it this way, from Newton's third law, I will have to reverse it and put it like that on the other body. So this is Rc. Similarly, this is Rc, and let us take this. This will be Rs. So these are the forces, compressive forces acting on the respective rods there are. Naturally, this is also in equilibrium, so it is not. It is very easy to see that the reactions mobilized at the bottom of these rods will also be of equal magnitude Rc. Hence, it is easy to see that each and every rod is in compression, and the edge rods, that is namely this one as well as this one, is undergoing a compression of Rc kilonewton, and the middle one is undergoing a compression of Rs. All right. So now, can we solve this using the principles of statics is the first question. So we have Rc that is unknown, Rs that is unknown, and W which is again unknown. Hence, there are three unknowns in this problem, which is what makes it statically indeterminate. Hence, there is a need for us to bring in the deformation picture into this problem. All right. So that being said, if I were to observe this, this block is given to be rigid. Now, under the action of this rigid block, under its weight, it would have shifted somewhere over here, let us say. So it would have shifted somewhere there. By virtue of that being rigid, the change in length in the copper rod will be same as the change in length in the steel rod. which is what is the essential compatibility of this question, compatibility condition of this question. So let me take a copy of this. So for this question, the compatibility condition compatibility of displacements gives us that delta, that is change in length in the copper rod. Change in length in the copper rod will be same as change in length in the steel rod. So this is my compatibility condition. So I have got two conditions. Sorry. So I've got this one condition. All right. Now, what do we know about this change of length? I know that this is the force being applied. So therefore, delta C is nothing but RC LC by AC EC. Similarly, delta S is RS LS AS ES. All right. So this and the compatibility condition gives us from here, we know that this is actually equal to this quantity. So RC by AC actually represents the stress in copper. So therefore, the stress sigma in copper into LC by AC by EC is equal to stress in steel into LS by ES. So we have a relation how the stresses will get mobilized in what ratio. So therefore, sigma C is nothing but LC ES by LS EC. I'm sorry. Sigma C is EC LS by ES LC into sigma S. So we have this relation. Now our idea is to maximize the weight of this block, which is the constraint statement in this question. So in order to maximize the weight of this block, at least one or both of the rods have to reach its peak allowable stress. So the maximum allowable stress in copper is given to be 70 MPa, and that in steel is given to be 140 MPa. So case 1, I assume, let copper reach its allowable stress. In that case, sigma C will be 70 MPa, and we have this equation to find out what sigma S will be. So therefore, sigma S will be ES LS. So I have to write these quantities. Let me bring them from here. So LC is 160 mm, LS is 240 mm, EC is 120 GPa, ES is 200 GPa, and then I have area of copper is 900 mm squared, and area of steel is 1200 mm squared. So this is the given information. So this much I have from the question itself. So based on this, Let me take it here. So based on this given information, I can back calculate sigma s as Es, which is 200 E3 into Lc, which is 160, divided by Ec is 120 E3 into Lc is, sorry, this should be 240. So from here we get sigma s equal to the reciprocal of this quantity, which is ESLC. ESLC by ECLS into the stress in copper, which is 70 MPa. So this comes out to be 200 into 160 divided by 160 into 240, 120 into 240 into 70. So this comes out as 77.78 MPa. And this we can see is below the allowable stress in steel, which is 140 MPa. So this possibility is definitely not ruled out. So we have to see, in order to maximize it, which possibility will actually hold good. So this is all right. So let us say case 2, that steel reaches its allowable stress. In that case, sigma s is 140 MPa. And then using this relation, we'll have sigma c equal to EC, which is 120 E3 into LS 240 divided by ES into LC, which is 160 into 140 MPa. So therefore, sigma C from here will come out to be 120 into 240 into 140 divided 200. So 160. So this comes out to be 126 MPa. And we can clearly see this is greater than the allowable 70 MPa. So therefore, case 2 violates our constraint. That it has to be within the allowable limit. So therefore, we know clearly from here that the maximum stress that can mobilize in copper is 70, and consequently, given the compatibility of this arrangement, the maximum stress that can be mobilized, that can get mobilized in steel is 77.78. So let us see what the question is asking. The magnitude of stress developed in copper rod and in steel rod. So we readily have the answers here. So for the copper rod, it is 70. For the steel rod, it is this quantity. And the maximum weight of the block is asked. So for that, we can use this constraint equation for the weight of the block. Now, weight of the block, we will be using this. Now we know that RC is nothing but sigma C AC, that is whatever stress it is experiencing into the area. So therefore, this is 2 sigma C AC plus sigma S AS equal to W. And the left side is entirely known. So this is 2 into 70 MPa into AC is 900 plus sigma S is 77.78 into AS is 1200 mm squared, which comes out to be, so therefore W maximum comes out to be 2 into 70 into 900 plus 77.78 into 1200. And since we have been asked in kilonewton, so we can report that in kilonewton, which comes to 219.3 kilonewton. So this is the maximum weight such that the arrangement respects the constraint to be within the allowable limits. All right. So we'll move a little quicker because there is a lot of ground to cover and I only barely touched the first question. So this question says the state of stress at a point is given as follows. Sigma is this. So we know how to identify this. Consider a plane passing through the point whose normal has the direction cosine 0.25, 0.5 and m. Now this question says it's a unit normal. And the direction cosine, two of the direction cosines have been given and the third direction cosine is given to be m. But it is quite easy for us to find out what the third direction cosine is. So this is a unit normal. So therefore its magnitude is unity. So therefore 0.25 squared plus 0.5 squared plus m squared root over the entire thing is equal to 1. So therefore m can be back calculated from here as 1 squared minus 0.25 squared minus 0.5 squared root over, which comes to 0.829. So therefore n, the vector, is actually 0.25, 0.5 and 0.829. All right, so given this, we have been asked on this very plane, what are the traction vector components, what is the normal stress and what is the magnitude of the shear stress. So it is easy for us to find out using Cauchy's formula. So using Cauchy's stress formula, we have this acted upon by, we have that matrix acting over this vector in order to give the traction vector at n. So this will be, the x component is just this will give us a 3 by 3 vector, and the x component, y component, z component are what are asked. So I will leave it to the users to do this matrix multiplication themselves. I will simply write the answers. So minus 700, 400, 600, 400,000, minus 600, and then this is 600, minus 600, and minus 400. 2, 3, 0.25, 0.5, 0.829. So this comes out to be 522.4. This is 102.6, and this is minus 481.6. Now the normal stress in the plane, we know the normal stress is nothing but Tn dotted with n. Why? Because if we have a plane like that, say we have a plane like that, and Let this be the traction vector on that plane, which is characterized by its unit normal n. So the normal stress will be the projection of this stress vector onto the normal, which is the dot product of both. So therefore, this will be these quantities 522.4, 102.6 minus 481.6 dotted with this vector dotted with normal. So therefore, sigma n on this plane is nothing but minus 217.34 MPa. Now it is easy for anyone to do the dot product. This is just the multiplication of the corresponding quantities and the sum of the individual components. The magnitude of the shear stress, now we know that this will be made up of two components like that. One we have found out. What is the other? It is this minus that, which is shear stress on plane n is root over the traction magnitude squared minus sigma n squared. So I leave it for the users to, I leave it for the viewers to take a shot at that. All right, so let us look at this question. The 3D state of stress at a point in MPa is shown. It is further known that two of the three principal stresses are 15 MPa and plus 1.81 MPa. So the principal stresses, two of the three are known to be 15 MPa plus 1.81 MPa. This is also plus. And then we have some sigma. I am not labeling it specifically as 1, 2, 3 because I don't know the third quantity. And we must always note that sigma 1, sigma 2, sigma 3 should always be labeled in the algebraically decreasing order. Since I don't know the third quantity, I don't know where to put it. So I am just simply labeling it sigma presently. Let it be sigma p for the sake of that being a principal stress. So the question asks, what is the minimum principal stress for this stress block? So this is a question for us to understand how to actually interpret stress cubes. So we have the positive x phase, we have the positive y phase here, and then the positive z phase here. And then the other sides of the cubes are negative phases. So I know on the positive phase, it undergoes a compression of 12 MPa, compressive stress of 12, and then I have shear stress like that. So this is the x phase and the shear stress is acting in this direction. So this actually is tau xy. So from the stress cube, what is it that I can interpret? For the stress tensor, if I were to populate this, I know that sigma xx is minus 12, tau xy is this quantity, which is 5. And I know that my stress tensor is symmetric, so two quantities I can populate. Now, on the face x, is there any shear in the z direction? There is no shear, therefore it is 0. Now coming to the y face. Is there any normal stress acting on the y face? No. So therefore sigma yy is 0. And this 5 is automatically taken care of here. In the z direction, there is no stress on the positive y face. So therefore this is also 0. And this is 0 by virtue of symmetry. Sigma zz is what we want to see now. So on this face, on the positive z face, there is a tensile normal stress of 15 MPa. So this is 15 MPa. So we have the actual stress tensor for this problem written. Now what I have been asked is what determine the maximum principal stress. Now that I know this, I can calculate the principal stresses easily by using the characteristic equation. But let me not go that further. Let me simply use the invariance. I know that for a stress tensor, the trace of the stress tensor is an invariant, which is the first invariant. So therefore, using I1 equal to trace of sigma, which is minus 12 plus 0 plus 15, which is equal to 3 MPa. So the trace of the matrix, that is the first invariant, is 3 MPa. But I also know that my some of the principal stresses also have to add up to the same quantity because it's an invariant. So it is 15 plus 1.81 plus sigma p equal to 3. So therefore, sigma p can be calculated from here as 15 plus 1.81 equal to 3. So this comes out to be minus 13.81 MPa. Now that I know the value, now I can confidently label them with this being sigma 1, with this being sigma 1, this being sigma 2, and the negative stress being sigma 3. So therefore, this is sigma 3. Alright, so the minimum principal stress here is this quantity. So the question says the minimum principal stress. It may well have said the third principal stress. The value of each of the diagonal elements of the hydrostatic stress tensor is what in this case? So let us recap what is hydrostatic stress tensor. So any stress tensor can be decomposed as hydrostatic plus deviatoric. So if sigma, this is hydrostatic plus deviatoric. Let me write it a bit neatly. Sigma is deviatoric. Sigma hydrostatic, we know it is I1 by 3 into I. This is a notation for identity matrix, which is all the diagonals as 1. So therefore, I1 is 3 MPa already. So I1 by 3 is 1 MPa. So therefore, this is 1, 1, and 1. So this is my hydrostatic stress tensor. So the question is asking the value of each of the diagonal elements of the hydrostatic stress tensor is 1 MPa. Naturally, the deviatoric can be easily found. This is the actual stress tensor. Which is equal to this plus deviatoric. So therefore, deviatoric is nothing but the difference of these two minus this quantity, which comes out to be minus 13,505 minus 1, 0, 0, 0, and 14. So I have my deviatoric stress tensor with me now. So now the question asks, what are the invariants of this deviatoric stress tensor? And there is a reason behind asking this, because the in the later portions, when we discussed the theories of failure, the von Mises theory has essentially something to do with the invariants of the deviatoric stress tensor, mainly predominantly J2. So that is why it is also mentioned in the lecture that it is called J2 theory, the theory of failure for metals. That being said, now that we have the deviatoric stress tensor with us, let us find out what its invariants are, which is very straightforward. So the invariants J1 is trace of this quantity, which is nothing but the sum of the diagonal elements, which will be identically 0. Why? Because deviatoric stress tensor is essentially deals only with shear stresses, and the normal stresses don't appear. J2 is the determinant of these four plus the determinant of these four plus the determinant of this, which is equal to 13 minus 25 minus 14 minus 13 into 14, which comes out to be minus 208 MPa squared, because it's a product of two stresses. Similarly, J3 is nothing but determinant of, in fact, it's not trace, but it is just determinant of this. Which comes out to be, I'll just find it using the calculator, which is a bit easier. So this is minus 13, 5, 0, 5, minus 1, 0, 0, 0, 14. Minus 14, 14. So I have the determinant for this case. It will be minus 13. Hi, Kokula, can you mute your mic, please? Yeah, thank you. Thank you very much.
Okay.
So this is the determinant of this matrix. It is minus 13. Just a moment. Minus 13, 5, 0, 5, minus 1, 0, 0, 0, and 14. So the determinant of this matrix is minus 168. MPa cubed, actually speaking, because it is the product of three stresses. So we have found out the J1 J2 and J3 for this problem. Hope it is clear. Alright, so let us look at this question. It says Pepsi cans have a mean diameter of 65 mm and a thickness of 0.15 mm. So therefore, if I were to cut, let me use another color. Let us say that I cut the can like that and look at it this way, artificially cutting, looking at it has some thickness. Now, this is extremely thin. So the thickness in this case is given to be 0.15 mm and the beam diameter from the center to the thickness of this sheet is given to be mean diameter. So I need to go both ways. So this is given to be 65 mm. These cans are sealed at an approximate internal pressure. So pressure internal is 220 kPa. Based on this, answer the following for a point A. So we have one point A on the surface of the can, on the outer surface of the can. So what is the Hooke stress induced at this point A? So we know that Hooke stress is PR by T, which is 220 E3 into R. R is the mean radius, which is 65 by 2, divided by thickness, which is 0.15 mm. So therefore, sigma Hooke will be 220 E3 into 65 by 2 divided by 0.15. Just a moment. Yeah. So this is given to be kPa. Now we have to represent that in MPa. So this will be 220 into e power minus 3. We have to go this way rather than that way. Into 65 by 2 by 0.15. So this comes out to be 47 MPa. So the Hooke stress is 47.46 MPa. Now the longitudinal stress is PR by 2T, which is half of this quantity. So I can clearly see from here that it is 23.83. The best estimate of the absolute maximum shear stress at this point is what? So we know that sigma 1 here is 47.6 MPa. Sigma 2 here is half of that, which is 23.83 MPa. Yeah. And since it is in the outer surface, the point is in the outer surface, we can clearly see that it is a free surface. So therefore, there is no normal stress here. So therefore, sigma 3 is actually 0. So for this question, if I were to draw the 3D Mohr circle representation, so I have one point at 65, one point at 32. So this will be one of the Mohr circles, and this will be the other Mohr circle. Actually, this will be equal. So I can just make this a little bit bigger. Yeah, it will be like that. So two of the three Mohr circles is like this. The third one will actually be this one, because sigma 3 is 0. Sigma 1 and sigma 3 circle will be this. So now from here we can see that the absolute maximum shear stress will be the maximum radius, the radius of the biggest Mohr circle, which will be nothing but sigma 1 by 2. So therefore, tau max is nothing but sigma 1 by 2, which is again 23.83 MPa. So when we design, we should ensure that we don't account just for sigma 1 and sigma 2 and design it for the maximum stress, because we can clearly see by virtue of sigma 3 being 0, our absolute maximum shear stress will actually be double that quantity. So I hope that is clear. The state of strain at a point in a plane is depicted by the Mohr circle as shown. So we have a Mohr circle which for strain, where the this axis, horizontal axis represents the normal strain and the vertical axis represents the shear strain. More precisely, it represents the tensorial shear strain. So the engineering shear strain is just double of that. That is why in terms of engineering shear strain, it is half of that. All right. So if point A on the Mohr circle, so we have one point A on the Mohr circle, if that represents the x direction, so we have an element, this is the x direction, and then we have some normal and shear strains over there, which is plotted here. And this is given to be the x plane, so to speak. So using the knowledge of the Mohr circle, locate the y direction. How will the y direction be? Physically, x and y are separated by 90 degrees. So in the Mohr circle, it will be separated by 180 degrees. So therefore, this, let this be B, represents the y direction. So far, so good. The magnitude of the distance of the center of this Mohr circle from the origin is what? So we have this at 50, this as 20, and this is 0. So I know that the center of my Mohr circle has the ordinates epsilon 1 plus epsilon 2 by 2, comma 0. With this being epsilon 1, this being epsilon 2. So it is nothing but 50 plus 20 by 2, which is 35, comma 0. So the magnitude of the distance is 35 microstrain. What is the radius? Radius for this circle can be easily seen to be 50 minus 20, 30 by 2, which is 15 microstrain. Now that we know this is the x plane. So what is the normal strain in the x direction? It will be this quantity. That is the normal. This is my shear. So how can this be found? Let me take the Mohr circle from here. So what essentially we are saying is this is the x plane. So if I have this triangle, whatever this quantity is added by with the center of the center ordinate will actually give me epsilon xx. Therefore, epsilon xx is nothing but epsilon 1 plus epsilon 2 by 2, which is the ordinate of the center, plus epsilon 1 minus epsilon 2 by 2, which is the radius, into cos. This is given to be 60 degrees. So this is cos 60 degrees. So what will this come out to be? Where epsilon 1 is 50 microstrain, epsilon 2 is 20 microstrain. So therefore, epsilon xx comes out to be 50 plus 20 by 2 plus 50 minus 20 by 2 into cos 60, which is coming out to be 42.5. Now, what is the value of gamma xy is asked. Now, it is easy to see from here that this distance is, excuse me, that this distance is actually gamma xy by 2. So therefore, epsilon 1 minus epsilon 2 by 2, which is the radius, into sine 60 is actually gamma xy by 2. So therefore, gamma xy is 50 minus 30 sine 60, which is, I'm sorry, this is not 30, this will be 20. 50 minus 20 into sine 60, which is coming to 25.98 microstrain. Yes.
Hello,
Yeah, please go ahead. Yeah.
sir.
Yeah.
Sir, actually, audio it is difficult, sir. I am not unable to hear, sir. Sound is.
Oh, yeah. So we have calculated tau xy equal to 25.98. Now we have to calculate what is the value of epsilon yy. Now from here we can see that this is the y direction. So epsilon yy is the ordinate of this point, which is total center. We know from here this is also 60 degrees. So this is the radius. So we just have to subtract it instead of adding it as we did here. So if I were to take it there, for epsilon yy, I simply have to subtract this quantity instead. So this is nothing but 50 plus 20 by 2, 35, minus 50 minus 20 by 2, 15, cos 60 degrees, which is 35 minus 15 into cos 60, which is coming out to be 27.5 microstrain. So therefore this is, so I hope that is clear. So since we are lagging a bit, and I have to complete the question spanning the entire course, I will move a little fast. Consider this flat plate. So we have a flat plate as shown, subjected to stresses only the xy plane. So we have x like this, y like this, and x cross y is coming out of that flat plate. Determine the value of sigma y. This thing is subjected to some stress in x y direction. Determine the value of sigma y if the other measurements are given as considering all the out of plane stresses to be 0, meaning in the stress tensor whichever has a z dependence, it is 0. Only in plane stresses are there. So sigma y is what? In the question it is given sigma x is 278, tau xy is minus 64, and epsilon zz. Stress being absent in the out of plane direction does not naturally imply that strain will be absent because of Poisson's effect. So the Young's modulus and Poisson's ratio for this question, for this plate material is 210 and 0.3. It is given. So we know from our generalized Hooke's law, what is it that we know? Epsilon zz is nothing but sigma z by E minus mu sigma x by E minus mu sigma y by E. I am dropping the second subscript zz, xx and yy, that is understood. So for this question, sigma z is actually absent. So therefore, epsilon zz is actually equal to this quantity, which is minus mu by E into sigma x plus sigma y. So from here, it is easy to see that E epsilon zz equal to minus mu sigma x minus mu sigma y, or if I were to solve for sigma y from here, it will be mu sigma y is minus mu sigma x minus E epsilon zz, this whole divided by mu if I take mu to the other side. So this is my sigma y. So let us plug in the values here. So therefore sigma y is minus 0.3 into sigma x is 278 minus E is 210 E3 excuse me, minus 210 E3 into epsilon zz is minus 5.2 into 10 power minus 4. This entire thing divided by 0.3, and this is 4 power 4. So therefore sigma y from here comes out to be 86 MPa. So this question actually tells us how to actually write the generalized Hooke's law and solve for the question. Okay, let us look at the next one. A rod is subjected to, we have a stepped rod like this. Oh, this is a different question. Let us look at that separately. So this we have done it as 86 MPa. So this question says a rod is subjected to a uniaxial load. So we have a rod like that. It is subjected to a uniaxial load in the linear elastic range. And it is observed that the change in the stress, that for a change in stress of 210, the corresponding change in strain is 0.001. So therefore, let us say that the change in stress for a change in stress of 210 MPa, the change in strain is actually 0.001 microstrain. If the Poisson's ratio of the material is given to be 0.28, determine the modulus of rigidity, that is G equal to what is what is asked. So for this question, if I were to draw the stress strain curve, now we have been told that this is in the linear elastic zone. So this point is 0, 0. Now this is linear elastic. Within the linear elastic zone, it says if my change in stress is 210 MPa, then the change in strain is 0.001. So therefore, I know that the slope of this line is nothing but my Young's modulus. So E is given to be 210 divided by 0.001, which is E equal to into 10 power minus 5 or minus 6 to 10 MPa upon 0.001. All right, so this is 210 GPa. So from here we can see that the material is actually resembling steel. Now we have been asked the modulus of rigidity. We know that G is actually equal to E by 2 into 1 plus mu. Similarly, we know the bulk modulus K is E by 3 into 1 minus 2 mu. So using this relation, we can easily see that G for this material, the bulk modulus for this material will be 210 E3 divided by
or since we have been asked in GPA only, I'll drop that E3, 210 by 2 into 1.28,
which is 210 by 2 upon 1.28, which is 82.03 GPA. So that is the bulk modulus for this material. So let us look at this question. A stepped circular rod PQR. So I have a stepped circular rod like that, which has two different dias. So let me draw it first. Let this be the other one. Very well. So has a gap of 0.02 mm from the bottom. So it is not exactly touching, but there is a gap of 0.02 mm at the bottom at ambient temperature, at the temperature at which it is measured. So if I were to take this out and split it like this, presently there is no load acting on this, and we have not been given anything about the weight, so I will ignore the weight for the time being. Considering ES as the Young's modulus and alpha to be 12.5 microstrain per degree centigrade, along with the respective diameters, answer the following questions. So the magnitude of minimum temperature change in degree centigrade required to close the gap. So for this case, if this is L, let this be L PQ, or I will label this as 1 and I label this as 2. That will be much convenient. So this is L1, this is L2, and I have this is D2, this is D1. This is P1. So this much I know. Now what has been asked is, what will be the temperature change required to close this gap? Now if I were to heat this, what will happen? It will start expanding like that. And what will that expansion be? So delta L1 will actually be L1 alpha 1 delta T. Similarly, the change in L2 will be L2 alpha 2 delta T. I am writing for a general case where the materials are different. Now since the materials are same, the question asks for the gap to close. This quantity for the gap to close, delta L1 plus delta L2 must be equal to 0.02 mm. That is when the gap will close. So this plus this is equal to 0.02. But alpha 1 equal to alpha 2, since the materials are same, which is 12.5 microstrain per degree centigrade. So therefore, this comes out to be L delta T into L1 plus L2 is 0.02 mm. Therefore, delta T required to close the gap is 0.02 divided by this quantity into alpha, which is 0.02 by what is the total length L1 plus L2? It is 50 mm. So this is 50
into 12.5 E minus 6. So delta T required to close the gap is
50 into 12.5 E minus 6 inverse into 0.02, which is
32 degrees. So if I were to raise the temperature by 32 degrees, the gap will close. So far so good. So this is my answer for the first part. Alright. Now let me draw this again quickly. Yeah. So if now the next part asks, considering that the entire setup is uniformly heated by 50 degrees, heated to 50 degrees now, above its initial ambient temperature, whatever it was, we have heated it to 50 degrees instead of 32. 32 is when the gap will close. So we have heated it till 50 degrees. What are the stresses induced? So in such a case, what will happen? Now this is fixed like that. It would have undergone the change when the gap exactly closes. Now this is the condition where the gap closes, which is at 32 degrees. We have heated 18 degrees beyond this since we have gone till 50. So if it was left free, it would have expanded like this. But it is not, so it has to stop here. That means there has to be some compressive force offered by the floor which actually nullifies this expansion, which is our compatibility condition to find out the stresses. So let me take this here and let us separate this out like that. So this will be subjected to a compression. This is from the floor. Let us say RF is the force from the floor. So since this is in equilibrium, this will also be RF. Similarly, this is also RF, and the reaction, the pull that this is experiencing, or the push that this is experiencing, is also RF. Very well. And then this is now what the total change of length will be. It will actually, the physically what we will observe is 0.02 only. So therefore, compatibility states that free expansion of the rods minus change in length, or rather I should say minus contraction due to RF must be equal to 0 when this delta T is above 32 degrees centigrade. This is our compatibility. So therefore, this means that L1 alpha 1, or rather alpha delta T greater than 32 degrees minus RF L1 by A1 E1 plus L2 alpha, the same quantity, above 32 degrees minus RF L2 by A2 E2 is actually equal to is actually equal to 0. So I hope that is clear. At 32 degrees, this already closed. Beyond that, whatever we heat and the compression both add up to 0. So let us see what this value will come out to be. So if I were to take this common into L1 plus L2 minus RF into L1 by A1 E1 plus L2 by A2 E2 equal to 0. So if I were to take it to the other side, this will just be equal to this quantity. So therefore, the reaction force is actually equal to this divided by this quantity. So I leave it for when I post this sheet, I will be posting it with the answers. I leave it for the viewers to solve for this and find out. Once we know RF, we know the area of each of the individual rods. It is just a matter of dividing it in order to get the stress. So I leave it at that because there are more questions to cover and not much time. So I'll move on to the next question. Consider a circular shaft fixed at end A and subjected to torques at point B and point C. So at point C, we have a torque like that. At point B, we have a torque like that of 20 Newton meter. And at point C, it is 150 Newton meter. So the sign convention is given like that. How this is to be interpreted is this is the positive surface. This is the negative surface. Our positive Z axis acts in this direction. So on the positive Z, it will be this. On the negative Z, it will be like that. So we have 210 as Young's modulus and Poisson's ratio is 0.3. And when we cut this section at section we have a circular cross section of diameter 0.1 meter. What is the modulus of rigidity? It's nothing but E upon 2 into 1 plus mu, which is 210 by 2 into 1 plus 0.3, which is 2 into 1.3 to 210. So this comes out to be, so G is actually 80.77 GPa. So this much we have found out. What is the torsional rigidity of the material section? What is torsional rigidity? How is it defined? Torsional rigidity is GIP, which is 80.77 E3 into what is IP? For a circular section, what is the polar moment of inertia? It is pi d power 4 by 32. Which is 80.77 E3 into pi into. So this is 7.93 into 10 power 11 Newton mm square. So we have found out the torsional rigidity. Now the question asks, how will we draw the twisting moment diagram? So the twisting moment diagram, we will cut this section first. Let us take this section alone. For this, I have in fact, let me do it. I will just take two cuts and draw the twisting moment diagram. So let us quickly draw the twisting moment diagram. I have taken a cut like this. For this cut, according to the sign convention, this should be my twisting moment. Therefore, sigma fx fz equaling 0, not f, I'm sorry, excuse me. This is in equilibrium. So therefore, sigma mz equaling 0 gives me minus mt plus 150 equal to 0, or mt is 150 Newton meter. For portion BC, for this portion, wherever I cut, there is no other torque applied, so this will be constant positive 150 for portion BC. Now let us go to the next portion, like that. Here again, it is a negative surface, so my MT has to be applied like that. So sigma mz equaling 0 gives me minus mt plus 20 plus 150 equal to 0, or mt is 170 Newton meter for portion AB. Clubbing these two, I can see my twisting moment diagram for this problem will be like that. Where this is 150. In fact, I should have drawn it to scale. Yeah, this is better. So this is 150 and this is 170. This is positive MT along C. Excuse me. I hope this is clear. All right, so let us move on to this question. I won't solve this completely. I'll just give what the brief is. So a 10-meter long circular shaft needs to be designed at site to transmit a torque of 350 Newton meter. So MT to be transmitted is 350 Newton meter. The length is 10 meters. The material available is only aluminium, which has a Poisson's ratio of 0.33 and Young's modulus of 70 GPa, with a maximum permissible stress of 13 MPa. So tau max, maximum shear stress permitted is 13 MPa. How do I know it is only shear? We are talking about shafts presently, which are subjected to shear stresses. The design also requires the maximum twist of the shaft to be limited to 1 degree. So phi max should be less than equal to 1 degree, and this should also be less than equal to 13. As an engineer, explore the following design options for the design and answer the following questions. So we have been asked to design this. So what is the modulus of rigidity? This is clear. This is G is E by 2 into 1 plus mu. So I won't solve this because we have done this something number of times. 2 into 1 plus mu. All right. If a solid shaft is adopted, what is the maximum diameter of the shaft using the strength criteria? Strength meaning stresses should be within the limit. Stiffness criteria meaning deformation should be within the limit. So for strength criteria, what is my tau expression? It is for a solid shaft, it is 16 mt by pi d cubed. So therefore 16 mt by pi d cubed should be less than equal to 13 MPa, or in the limiting case we will equate these two. Therefore d is cube root of this 13, let this be sigma allowable. Sigma allowable. Right. So this will be 16 mt divided by pi sigma allowable. Cube root of that. Similarly, for the next part, it says first from stiffness criteria. What is stiffness? What is the rotation twist of a shaft? It is ml by mtl by g ip, and this should be less than equal to phi max, which is 1 degree. Now we should not forget that when we substitute this 1 degree must be substituted in radian. It will actually not be less than 1, it will actually be less than pi by 180. So therefore, which is equal to pi by 180. So therefore, if I were to substitute this is mt L by G that we found into 32 pi d power 4 less than equal to pi by 180. And in the limiting case, we will equate it to this. Rest of the quantities are all known. Only d is not known, which can easily be calculated from here. So I leave it for the viewers to do that. Now we have, from strength criteria, we have one diameter. From stiffness criteria, we have one diameter. Which is the one we will adopt as the minimum diameter? Minimum should not be minimum of these two values. If let us say d from here comes out to be 50 mm, for example I'm saying, and d from here comes out to be 100 mm, we should adopt the maximum out of this. Because if we were to adopt the minimum out of this, the other criteria will anyway not hold. Because we have a direct dependence on that. So this will be the maximum diameter. Now there is also an option to have a hollow shaft instead of a solid one. So where all this will change, it will only change in this quantity IP. For a hollow and for a solid, we know how it is differentiated. So the same drill we have to do, except now the shaft is hollow rather than solid. So for the hollow shaft, let us say this is the hollow shaft. It's like that. Let the inner diameter be di. Let the outer diameter be d naught. Now di by d naught is given in the question to be 0.8. Let us call this ratio r. Then IP is actually given by pi d outer power 4 by 32 minus pi d inner power 4 by 32. It is the difference of two circles, which is nothing but pi d outer power 4 by 32 into 1 minus this r power 4. So when it is solid, this quantity will be absent. Why? Because if the inner diameter goes to 0, we can clearly see R becomes 0. If I put R0 here, it will get back to the moment of inertia of a solid shaft. So this is all the differences. So I encourage the viewers to attempt this problem with that background in mind. A blade is placed in a hacksaw. So we have a blade that is placed in hacksaw and tightened. So this screw is tightened so that the blade is in tension. Is in uniform tension of 250. The hacksaw frame has this frame has a section like this, which has which has dimensions as shown, and is made of alloy steel of thickness 1.5 mm. The maximum permissible stress in this material is 215. So the question asks, due to the tightening of the blade, the frame of the hacksaw experiences which of the following? So this was also discussed in one of the live sessions. Since the hacksaw blade is experiencing tension, it will apply a force like that on the frame. Here actually I am not, or rather what I will do, from the same question, let me take an image of this. Now let me put it here. For this case, let me remove the blade to draw the free body diagram. I have removed the blade, and the blade would actually be applying a force like that. This is 250 Newton, what we have applied. Now I know if I were to resolve it to this will get directly applied like that. In addition, there will be a couple like this, whose value is 250 into 80 Newton mm. So the section actually undergoes axial compression and bending. The moment of inertia of the frame which would resist bending is about this axis. So it will be IZZ, which is equal to 6 into 12 cube by 12 minus the inner dimension. What is the inner dimension? This is 1.5 mm thick. So 3 goes. So this is 3 and this is 9 minus 3 into 9 cube by 12. This is what resists bending. The magnitude of the axial stress is sigma is compression. Axial force is minus 250 by what is the area? It is 6 into 12 minus 3 into 9. And the question asks for its magnitude. This is my axial compression. What is my bending stress? From flexure formula, I know my bending stress is nothing but mb by izz into y. So what will be the maximum bending stress when y becomes max? Y is the total depth by 2. So actually speaking, this will be mb max by z, where z is section modulus. And we just have to add up the two in order to find out whether it is within the permissible limits. So I encourage the viewers to attempt this problem. Excuse me. Excuse me. A high strength aluminum I-beam is further strengthened by riveting a steel plate on the top. The Young's moduli of aluminum and steel are so and so, 70 and 210 respectively. The rivets are not shown here. If the beam section is subjected to a bending moment of plus 60 plus 50 kilonewton meter is the bending moment that is getting applied to this section. Using the transform section method, find out what these quantities are. If the steel is transformed into aluminum, determine the transformed moment of inertia, and then stresses. So steel is presently of width 150 and depth 8 mm. Now if I were to transform this, if you revisit the session on transformed area method where I had solved it using both curvature as well as transform section method, we saw why the transform section method is more elegant, although it waters down to the same thing. It's a matter of interpretation. We saw that what we do is actually we scale this by ES by EA in order to convert everything into aluminum. If I have to convert everything into steel, I have to horizontally, I have to shrink the aluminum beam only horizontally by a value of EA by ES. So since this question is asking us to do it in terms of aluminum, the transform section will be something like that. So we have the I here. It is something like this. Hope it is symmetrically placed. And then now the entire thing is aluminum. So this is my transform section. So how do we go about finding the moment of inertia? This will have a centroid. This is y bar. So we have to find y bar first. How do we do that? Sigma A y bar by sigma A. Once we find the centroid, we can use our parallel axis theorem in order to find out, because these are simple shapes. These are just rectangles stacked one over the other. Excuse me. Rectangles stacked one over the other. So the moment of inertia about its centroid. Now we can actually see it won't be at half the distance because there is more material towards the top, so it will actually pull the centroid towards itself. Now this is done, it is just a matter of applying the flexure formula. How? Flexure formula is mb by izz equal to minus sigma x by y equal to E by R. However, we are not dealing with this portion of the flexure formula. So once the bending moment is given in the question, Izz is what we have to calculate for this transformed section, where this width is 150 into ES by E aluminum, which is 3. This quantity equal to 3. So therefore this will be 4500, 450 mm. The rest everything remains the same. So once we find out Izz and once we find out MB, sigma x is just a linear function of y, this y. So what is the magnitude of the maximum bending stress in aluminum? Mind you, aluminum is this portion presently. The portion on the top is transformed aluminum. or transformed steel, I should say. It is not actually aluminium. So the maximum stress can occur here or at the bottom for aluminium. So we have to see which is more and report that. As for the magnitude of bending stress in steel, it will naturally be here because steel is only on the top. So it will be Y equal to Y bar. And that will be the, from this expression, whatever stress we get will be the stress in the transformed section. In order to find it in the actual material, we will have to again multiply this by the reciprocal of this in order to find it out. So you may visit the section where we have discussed unsymmetrical bending and give this question a try. So I'm just covering the basics of what are the concepts involved in solving this, because my idea is not to solve every question threadbare, because I'll run out of time. Already we are nearing the closure and there is some more ground to cover. A simply supported beam is required to support a load shown. So it is like this. It is a 4-point bending beam where there are two symmetrically placed loads of 50 kilonewton. Material property, etc., is given. Maximum yield stress is given. Neglecting the self-weight, what is the minimum depth of this square section? So this is a square beam. What is the minimum depth to have safe operations? So I know what is my bending moment maximum. This is a 4-point bend beam. So I know I have two reactions which are also 50 kilonewton. Now, how does the bending moment diagram for this beam look? It is like this. So the maximum bending moment is over here, which is constant. So this is the shear span. So the maximum bending moment is this 50 into 2. So maximum bending moment is 100 kilonewton meter for this problem. That being said, if I have my maximum bending moment by Z, the section modulus of the square should be less than equal to, what is the permissible stress given? 210 MPa. Let us say this is the square section. If this is of depth d, it is of width d. So therefore, the section modulus is nothing but d into d squared by 2, d squared by 6, or rather, I won't calculate it like this. Izz d into d cube by 12. Section modulus is Izz by y max. This y max is nothing but d by 2. So therefore, the section modulus is d into d squared by 6, which is what needs to be substituted here. MB max, we know it is 100 kilonewton meter, and we can easily find out what is d from this expression. Now they are saying that given the depth adopted for the square is 150 mm, whatever comes from design, that is fine from the previous one, but we have adopted 150 mm. Now I have to answer what is the absolute maximum bending stress. So it is just the reverse of this. This was peaking. Now this will be sigma xx, and z gets calculated based on 150. And what is the stress is what they are asking. What is the absolute maximum shear stress? In this portion, there is shear of 50 kilonewton. I know that for a square section, the variation of shear stress is like this, where the maximum value is actually 1.5 times the average. (1.5) times tau average, which is 1.5 times the maximum shear stress by area. Area of a square, we know. What is the maximum shear force that is getting applied is 50 kilonewton, and 1.5 times of that. How many times? What is the ratio of the absolute bending stress to the absolute maximum shear stress? So we just need to provide a ratio of these two. The idea behind asking this is so that the people who are solving this understand and reflect on the fact that how big bending stress is compared to the actual shear stress. So I encourage you to solve this for yourself and see how much it will come out to be.
Okay, so this was one of the questions that was asked in the assignments, and there was a request in the discussion forum to discuss this question in the live session, so I'm taking this up. Let us look at this question. It says consider a propped cantilever beam having a flexural rigidity of 1.4 into 10 power 14 Newton mm. So EI is basically 1.4 into 10 power 14 Newton mm squared. Fine. That is loaded as shown. Neglecting shear effects, we have to answer for the question. So what is it that we have here? We basically have a propped cantilever beam which is fixed at that end, and a prop, so to speak, a roller is put at B. It has a load P, concentrated load P at the midpoint C, and it has a couple that is applied at the propped end. So the first question says, let UP be UP bending and UM bending be the strain energies due to the bending, considering the beam to be loaded only with, that is, we have decomposed these two cases. Basically we are having only P applied first, and then we are having only M applied first. M applied. So the question asks, let U total be the strain energy of this system where both are applied simultaneously. So the question asks whether these two strain energies add up to this case. So this is U total. Whether these two simply we can add to get that is the question. Now we know how is strain energy defined for bending. Strain energy denoted by U, capital U, is denoted as mb squared by 2ei dx over the length L. So we are able to see it's a quadratic function in B. So will this add up to the total strain energy is the question. So I will just take a small detour, a basic example let us look at to see whether this will add up or not, and we can extend the same logic to this question as well. So let me take a cantilever beam presently. Let me take a cantilever beam. Let this be length L, and at the end let us apply a couple M. Now I'll take the same cantilever beam. Instead of the midpoint, instead of the end, let me apply the couple at midpoint. So this is case 2. And let case 3, let me shift it here, and let case 3 be when both are applied. Alright, so far so good. So for the first case, what will the strain energy be? We know at any section we cut, our bending moment is going to be equal to M. So therefore, strain energy for this system is nothing but integration of from 0 to L M B squared by 2EI dx. Now for any section, for any x, MB is equal to M. So therefore, let me call this case 1, let me call this case 2, and let me call this case 3. Very well. And let me move this a bit here. Alright. So U for 1, U1, let me say, it is nothing but M squared by 2EI integration of dx from 0 to L, which gives me U1 is M squared L by 2EI.
So I have got the strain energy for the first case. Now let us look at the second case. For this case, we know that from, by the way, x I am starting from here. So it starts from x equal to 0 to that way. It doesn't make a difference. Here, for x equal to 0 to x equal to L by 2, mb is 0. There is no bending. From in this section, there is no bending moment. So therefore, u2 is basically from L by 2 to L mb squared by 2ei dx, which gives me, again, for this portion the bending moment is again m, same as the previous one. So m by 2ei integration of L by 2 to L dx, basically this will be a square. So therefore u2 is nothing but m squared by 2ei into L by 2, or u2 is m squared L by 4 ei. So we have got the strain energy for the second system as well. Now what this question is driving towards is the simple fact whether if we add these two, whether we will get the strain energy of this. So let us work it out and see for ourselves what will happen. So for this case, from x equal to 0 to x equal to L by 2, from x equal to 0 to x. So for this portion, the bending moment mb is m, and for x equal to L by 2 to x equal to L, mb is basically 2m. So it has to, any section cut here would have to support these two moments, so that will be 2m. So in that case, u3 will be integration of x equal to 0 to L by 2 m squared by 2ei dx, plus from L by 2 when we go to L, it will be 2m squared by 2ei dx. So that is all there is. So let us quickly simplify this. So this gives me m squared by, again, L by 2, so this will be 4ei plus 4m squared by 2ei into L by 2. So there, this gives me, the 2 cancels out, so 1 plus 1 by 4, so this is 5 by 4. So u3 comes out to be 5 by 4 m squared L by ei. So we are seeing something interesting here. When we apply these individually, it gives me 1 by 2 and 1 by 4. So we know that 1 by 2 and 1 by 4 is nothing but 3 by 4. Whereas when it is simultaneously applied, this is greater than the sum. So, and why does this happen? This is because of the non-linear dependence, the power of 2. So we know that a plus b whole squared is not equal to a squared plus b squared. It actually has some additional terms here because of the quadratic nature. So this implies that whenever we apply energy methods to any question, it is essential that all the loads are applied onto the system, and only then we should embark upon calculating the strain energy. Just because superposition is valid does not mean sum of strain energy will actually give you the strain energy of the entire system, unless and until all the loads are present in the system. So I hope that is clear. So u total is greater than UPB plus UPB plus UMB because of the additional terms, which we just saw using a simpler example. I could have done just the same for these two cases as well, but it would have been more cumbersome because the reactions come into the play. But the idea behind asking this question was to understand that these two don't sum up to the total strain energy because of the non-linearity present. So I hope that is clear. Now obviously we can see that if we were to solve this question, the second part, which has the magnitude of the reaction at B using the energy method, basically the fictitious load method. So I will have to apply RB is anyways there, plus I have to apply some RB fictitious load, and then calculate the entire strain energy of this system. Once that is calculated, I differentiate that with respect to RBF, and then set that equal to 0. So there will be a moment here, there will be a moment here, which I have to separately integrate, and there is already two terms here adding to M and P. So we can clearly see that once we use energy method for this question, strain energy method, it is going to become very cumbersome, which is why clearly in the question, the first question confined itself to asking how strain energies vary, and that is where it ended. The second question is asked to solve using the superposition method. But nonetheless, in the interest of clarity, we will at least look at this solution using the superposition method as well as moment area method, so that it becomes clear. So this question is asking what is the magnitude of the reaction at the roller B. So for this prop cantilever, which has this and this applied, we have a prop, so this will have some RB. So the question asks what is this? Find this out using superposition method. So let us try and look at how that is to be done. Alright, so I have this here. Now let this be reaction. Let me replace it at this end. Let this be some RB, which is my interest of to find that out. So if I were to apply superposition, I can take this as a superposition of basically three problems. So I have a beam like that with a force P applied here at L by 2, and this would deflect. Basically this would deflect something like that. Let us say it starts from here, it will be 0, and then it will go up to some value like that, and from here on it is going to be straight because it is just a rigid body motion as explained in the lecture as well. So this is straight, this has a, so this is a higher order curve, and the rest of the portion is straight. So let me make it like that. Alright, I suppose you are able to appreciate that. Yeah, that is somewhat better. So what is this quantity? This is due to, this is delta AC, and then I have the remaining quantity. This is basically theta C into L by 2. This quantity is theta C because the slope here, which is theta C, is the same as slope here, theta C, because this portion is actually straight. And delta AC, we know it is the deflection of a cantilever, smaller cantilever with length L by 2. So this is due to P. Now let us see the same thing due to M. If only M were applied here, so I can take the same curve, except it will be 0 and I'll have some non-zero value here. So it would be, the deflection would be something like that, which is delta AB due to M. This is delta AB due to P, theta due to P. I hope that is clear. And once I apply only RB into the system, it will be its mirror essentially this is due to M. So due to RB, I have the beam like that. I basically have the deflected shape, something like that. Put this here. Yeah, this is something like that. So this is delta AB due to RB. So the compatibility states that adding all the three up, this plus this, actually leads to zero deflection at the end B. So therefore, using superposition, we have this quantity, I'm sorry, we have delta AC due to P, delta AC due to P plus theta C due to P into L by 2 plus delta AB due to M minus delta AB due to RB is equal to 0. Basically, I have just added these quantities. This is the total deflection due to P. This is the total deflection due to M. Both are downwards. And RB tries to nullify that to bring it back to 0. So that is essentially what I've written. So substituting these from the standard equations we know. Basically PL cubed by 3EI and PL squared by 2EI for the slope. ML squared by 2EI for the deflection and so on. For the moment and so on. So delta AC due to P is P into L by 2 whole cube by 3EI plus P into L by 2 whole squared by 2EI. This is theta C due to P into L by 2 plus what is that due to moment? It is ML squared by 2EI. So M L squared by 2EI minus RB L cubed by 3EI equal to 0. So right off the bat I can cancel out EI's totally. So let me write that up. So this is PL cube by PL cubed into, I have some fraction here which will be 0.5 cubed by 3 plus 0.5 squared by 2 into 0.5. So this is 5 by 48. So this comes to 5 PL cubed by 48 plus ML squared by 2 is actually equal to RB L cubed by 3. So let us remove L cubed from here. So basically I'll get 2 by L. So therefore RB is nothing but 15P by 48 plus 3M by 2L, or in other words RB is 5P by 16 plus 3M by 2L. So this is what we have got using superposition. Now let us try to solve the same question using moment area method and see if we get our answers right. So using moment area method, what is it that we have to do? First, we consider the total system. We have T here, we have RB acting here, and we have M acting like that. So if I were to decompose this into three bending moment diagrams, I will have the first one like that. This is the first bending moment diagram, where this is PL by 2 and this is negative. So it will be like that. The second bending moment diagram is going to be because of the couple applied at the end, which is just going to be M constant throughout. And the third bending moment diagram will be a triangle like that. I'm sorry, 1 minute. It's going to be a triangle like that, which will be positive, and this will be RB into L. So these are the three so the total bending moment diagram of this entire system is going to be the sum of these three. So I have just put that individually, thus differentiating them into separate simple shapes, triangles and squares and so on. So now that that is done, I know how to calculate deflection at this point due to using moment area method applied on this bending moment diagram. Same goes for this and same goes for this. I just need to add everything up and equate that to 0, and I will get the equation for RB. So let us go ahead and do that. So using this bending moment diagram, delta, the free end is labeled B, right? So so delta at B will be area of this into this distance, moment of area of that. So that will be half into T, and by mind you, we have to go for M by EI diagram. So when we go for M by EI diagram, this will be half PL by 2 EI into L by 2 into what will be the distance of this centroid from the total end. It will be L minus 1/3 of this length, which is L minus L by 2 into 1 by 3. So this is the first deflection due to P, I should say. Now deflection at B due to M is area of this, moment of area of that about this distance, which is nothing but M by EI into L by 2. That's about it. For the third case, it is the moment of area of this bending moment M by EI diagram about this point, which is M delta B due to P, which is half into RBL by EI into L into 2 by 3 into L. Because its centroid is over here, this is 2/3 of the base. So I just need to add these quantities up now. So let us go ahead and do that. So this the compatibility states this plus this, and because here we have taken the negative, naturally the negative should appear here, minus, and this will be plus. I hope that is clear, because the nature of deflection of one case is opposing the other, and this is equal to 0, which means I have minus this quantity, minus of this quantity plus this quantity equaling 0. So let us quickly solve this. So what will this come out to be? So I can shift this to the right side. So let me consider this on the left side first. So what will that be? RBL cube by 3 EI is equal to, if I take this quantity, move it to the right, I get rid of the minus. I just have to calculate the rest, which will be nothing but 1 by 1 minus half by 3 into half. This is 5 by 48 again. 5 PL cube by 48 EI plus this is ML squared by 2 EI. So if I get rid of the flexural rigidity here, EI gets removed. If I were to divide the entire thing by L cube, I get 1 L here. Now if I were to take 3 to the other side, I have it like that. 3 into 5, and then I have this quantity. So what does this come out to be? So therefore RB from here comes out to be 5P by 16 plus 3M by 2L from the moment area method, which is identically same as what we got here using our simple superposition, because basically it is one and the same. We have just split that out and we are multiplying this out. So this quantity basically gives us the effect of load P and so on. So we can see that the same question can be solved using superposition as well as moment area method, leads to the same result. So I encourage, now that we have found out the reaction at point B, I encourage the viewers to actually try the same method to find out the deflection at point C. How can that be done? Using superposition, it is very clear. So at point C, I know what is the deflection due to this load. It is nothing but P into L by 2 whole cube by 3 So I get due to this. Now this will actually try to nullify. So when we are dealing with point C, we should basically take this point RB reaction here as well as a couple RB L by 2. So accumulative effect of these two will come at point C due to RP. Same goes for M. However, M is a couple which is a free vector, so I can move M from here to here and it will just be M equal to 3. So accounting for all this, we will get the deflection at point C. So I encourage the viewers to actually give it a try. And if there are any questions, you can always post it in the forum. So let us move on to this last question on buckling. I'll just give the essence of what it is. A 6-meter long column having a box-shaped cross-section with end support conditions as shown. So the end support is at the bottom, it is fixed. At the top, it is hinged. So when this comes down, the deflected shape will be something like that. I'm just exaggerating it and drawing. So rotation is allowed here, rotation is not allowed here. So for such cases, we know that L effective is nothing but 0.7 actual L. So based on this, it is subjected to a compressive load of 3000 kilonewton, that is 300 tons of load is taken by this column and its cross section is this way. So the question asks, the moment of inertia governing the column buckling is which one? So the cross section we can see that Iyy is actually greater than, we can actually see that Iyy is actually less than Izz if you calculate and see, because distribution of the area is more along the y direction, so Izz will naturally be more. So therefore, which moment of inertia will actually govern the buckling behavior, whichever is the least. So Iyy will actually govern. So Iyy calculation is quite simple. For this, it will be 250 into 150 cubed by 12. This would have been the case if it was solid, but it is not. So I have to subtract out the inner rectangle, which is 200 into 100 cubed by 12. So this will be my governing moment of inertia. Given the support conditions, what is the effective length? We have already discussed it here. The effective length will be 0.7 L. So the slenderness ratio is given by L effective by R, where R is the radius of gyration given by I minimum by area. And we found out I minimum is Iyy. So if we substitute Iyy and the area of the column here, what is the area of the column? Is the difference between the area of two rectangles. These two rectangles, what is this area? We can easily find out. So from here you will get R. L effective, we know it is 0.7 L. And the actual length of the column is already given in the question to be 6 meters. So it is just a matter of substitution and we can find the slenderness ratio. The column can buckle along which of the following directions? Naturally, when we have cut the cross section, we are seeing Y and Z like this. So X is along the column, along the height or length of the column, naturally it will not going to buckle. So along Y and Z, where could it buckle? We know that this moment of inertia about this axis is the least. Therefore, if it were to buckle, it will buckle along the Z direction. So this will be along the Z direction. What is the critical compressive load for this column to prevent buckling? So we know the Euler's buckling formula. We know which is the governing moment of inertia. We know what is L effective. So it is just a matter of substitution and finding it out. So I encourage the viewers to give this a try. Now this is one interesting point in this question which I just will briefly discuss before we close. If only translation, let us say that we had the column like that. Let us say the column was like that, where the rotation is allowed here. And let us say that the rotation is also allowed here. Not for this problem, I'm just generally saying. Or rather, let me restrict it. So I have restricted the rotation here and it is allowed on the top. Just a moment. It is allowed on the top. Now what this question says is, if only translation of the column in the Y and Z directions is arrested at mid height. So we are putting a stiffener at mid height of the column, keeping everything same, keeping the end conditions unchanged. What will happen to the critical buckling load is what is asked. Here, for this question, this is L, and from here we can actually calculate L effective. For this case. Now let us take the case where it is stiffened like that. So we have or rather what I should do is, so what we have done, we have placed something like this at mid height. So what will this do? This will make it buckle like that. At the end, it is still 0. Here, there is no arrest of rotation. It is only not allowing translation. So it is not allowing it to move. So displacement here is 0. This displacement here has to be 0. However, it will still allow it to rotate. This need not be straight. It will be something like that, or the opposite way. So this will actually be the buckling mode shape. It could either be this or the mirror image of that, the rotated image of that. So in such a case, what happens? This is L by 2 and L effective for this is, for this small column, for this small portion, here rotation is allowed. On the top anyway rotation was allowed. So this is behaving like a pinned short column. So L effective is actually L by 2. And for the remaining portion, L is L by 2. L effective is, I shouldn't say L is L by 2. What I mean to say is length is L by 2. So this is L by 2 and L effective for this second portion of the column. I hope you are able to appreciate that now top acts as a hinge, bottom acts as fixed. So it is just this column but half the height. So this will be 0.7 into L by 2. So for this portion, L effective is 0.7 into L by 2. Now how will we solve this? We know what is the critical compressive buckling load for the entire column. So if I were to calculate the critical compressive buckling load for both the portions of the column, top and bottom, given their different boundary conditions, whichever is least out of this has to govern my buckling. So this is all there is to constraining it in the middle. Now instead of this, if I had to put a rectangular stiffener like this would also arrest the rotation. Hence, this top portion will actually have hinge on the top, fixed end on the bottom. Similarly, for the bottom one, both will be fixed. If both are fixed, we know L effective is half L. So we have to analyze two different short columns when stiffeners are used, and then whichever has the least critical buckling load will actually lead to the buckling of the entire column, because we cannot say if the beam, if once this buckles, naturally it will precipitate buckling in the other. So whichever starts the phenomenon of buckling will govern the actual design. Other than this, I have nothing more to add. So I hope that people who have been following the sessions have got something of substance out of this. All right. So thank you for attending, and I wish people who are taking the exam, I wish them all the best. Good luck. Thank you. So this concludes all the live sessions for this course in the present semester. So perhaps in the next semester, someone else will offer the live session. So I hope you found the sessions interesting and it added some value to the learning experience. So thank you very much.
Thank you.
Yeah.
Thank you very much.
Bye. Bye. Thanks.